we're going to have ourselves a little mini unit here. Our state standards require us to be able to prove a few theorems. We've been proving two triangles are congruent, and then sometimes going a step further than that, proving two triangles are congruent, and then proving that, well, there's a set of corresponding sides that are congruent because of that, or a pair of corresponding angles that are congruent because of that. So now we're going to take a look at these four theorems that our standards require us to be able to prove. Okay? One of the problems that you run into when you try to prove theorems as you go through a course, I didn't want to prove these as we ran into them because we had never done proofs before. And I've tried it that way before, and it's difficult to prove a theorem when you've never even proven anything before. Okay? So these proofs aren't going to be near as difficult now as they would have been, 6 weeks ago or whenever we first ran into these theorems. On the other hand, what gets difficult, though, is you got to be careful and not use something that was a result of the vertical angles theorem to prove the vertical angles theorem. You know what I'm saying? So that gets difficult. And it's not so bad on these. We can avoid it. But just for future reference, if you go to college and you take a bunch of math classes, you'll learn to prove a lot of different theorems, not necessarily in geometry either, but lots of different theorems. And as you're going through the course, it all kind of makes sense and all, but then when you get to the end of the course and you're having to prove a theorem that you learned real early, it gets difficult because you have to think to yourself, okay, what did I know when I proved this theorem the first time? I can't use something that came later to prove something that came earlier. You see what I'm saying? Like we have corollaries sometimes from the theorem. Well, you can't use a corollary to prove the theorem because the corollary came from the theorem. That kind of thing. But it'll be okay now. I'm just warning you. All right. Remember the things that we can use as reasons in a proof. Okay? And let's go ahead and tackle the first one. So don't worry about any particular page in your book. Let's just take some good notes here. So we're going to prove the vertical angles theorem. And if you recall, the vertical angles theorem says if two angles are vertical angles, then they are congruent. Or sometimes we would just write vertical angles are congruent. And we've used that a ton of times, haven't we? We've set up equations using this. We've used it to help, get like a side angle side going or something to prove two triangles are congruent. We've used the vertical angles theorem a whole lot. Well, now we're going to prove that it's true. We've just kind of accepted it up until now. Well, now we're going to come up with a proof that it's true. So, if two angles are vertical angles, then they are congruent. Now, when you prove a theorem, you still need given information, a figure, what you're going to prove, okay? So, to prove the vertical angles theorem, and I started with this. I guess I should have written the given first, but for some reason I put the figure first. In that figure, and I didn't label that missing angle because I only want to work with one pair of vertical angles, okay? In that figure, angle 1 and angle 3 are the vertical angles. So they're the ones that I need to prove are congruent to each other, aren't they? Okay? And if I can do that, there's nothing special about angle 1 and angle 3 other than they're vertical angles. So if I can prove it for this case, I will have proven that vertical angles are congruent. Okay? All right, so draw the figure. Write down that we're given angle 1 and angle 3 are vertical angles. And we're going to prove that angle 1 is congruent to angle 3. And since there's nothing special about angle 1 and angle 3 other than they are vertical angles, by proving that angle 1 is congruent to angle 3, that will prove that if two angles are vertical angles, then they are congruent. All right, let's just stick with two columns for the time being. So we have statements, we have reasons. And what are we going to put in our first statement? Yeah, we're going to say that angle 1 and angle 3 are vertical angles, and our reason is given. Bless you. All right, so we can all get this far, right? So we can all make it, make a pretty good showing of it. Well, now let's make a plan, just like we did when we were trying to prove that two triangles are congruent. Let's make a plan on this. Well, look at angle 1 and angle 2. Angle 1 and angle 2 are a linear pair, correct? And linear pairs are supplementary, right? Well, then look at angle 2 and angle 3. What are they? Linear pair. And linear pairs are supplementary. So doesn't it turn out then that angle 1 and angle 3 are both supplementary to the same angle? And don't we have a theorem that says if two angles are supplementary to the same angle, then they're congruent? Yeah, we do. So angle 1 and angle 3 really are congruent to each other, aren't we? Okay? So, next step. Angle 1 and angle 2 are a linear pair. And how do we know they're a linear pair? Because we know what a linear pair is. So, definition of linear pair. Well, I can go ahead and put that angle 2 and angle 3 are a linear pair in the same statement because it's the exact same reason, the exact same thought process. Everybody with me? Okay. Now, this is where the details get a little, you got to be technically correct. Once we've said they're linear pairs, now we need to say that they're supplementary. So angle 1 and angle 2 are supplementary angles. Angle 2 and angle 3 are supplementary angles because if two angles form a linear pair, then they are supplementary angles. We ready to move on? All right, so I also put down here that was theorem 2.3, but I crossed it out because I don't want you to put it down. The only reason I put that down is because in our book, the vertical angles theorem is theorem 2.8. We can use this theorem because 2.3, well, it was before 2.8, wasn't it? You got to be careful. You can't use something that came after it. So we're good with that. We used a theorem that came before the one we're proving, so we're okay with that. All right? Now, since angle 3 and angle 1 are supplementary to the same angle, angle 1 is congruent to angle 3. And the reason is, if I can get rid of the screen, that angles supplementary to the same angle are congruent. And then again, I looked up that number, which was 2.6, to make sure I really could use it, and I could, so then I crossed it out. Now, that proof seems all nice and reasonable, doesn't it? Okay? Now, I'm not sure that you would have thought to prove it this way. I'm also not sure this is the only way to prove it. There may be other ways. But am I right, or do you think, I think I'm right, that we would have had a really hard time with that if we did the proof the same day we learned the vertical angles theorem. But I think now, even if you wouldn't have come up with that proof yourself, does it make sense? All right, any questions? Okay, So that's how we prove the vertical angles theorem. The next one we're supposed to be able to prove is the alternate interior angles theorem. And that's the one that says if two parallel lines are cut by a transversal, then each pair of alternate interior angles is congruent. So we need to prove that if we have two parallel lines cut by a transversal, that each pair of alternate interior angles is congruent. All right, so I made a new figure. I didn't use the one in the book. All right. So all we need to be given is that A is parallel to B. And then we're going to need to prove that each pair of alternate interior angles is congruent. So we need to prove that angle 4 is congruent to angle 5 and angle 3 is congruent to angle 6. Now, I'm going to do this. I'm going to prove this one pair at a time. Well, I'll show you what I'm going to do as we go through it. Now, you got to think back a little bit. When we learned the alternate interior angles theorem, the thing we had learned right before it was the corresponding angles postulate. Right before it, we had learned that if two parallel lines are cut by a transversal, then corresponding angles are congruent. So since we learned that right before we learned this, we're allowed to use that in our proof. Okay? So if we look at it this way, I forget which pair I proved first. All right, so let's look at it this way. Let's make a plan. Angle 2 is congruent to angle 4 because of the corresponding angles postulate. Okay? Well, angle 2 is also congruent to angle 5 because we just got through proving that vertical angles are congruent. So if 2 is congruent to 4 and 2 is congruent to 5, doesn't it seem reasonable that we ought to be able to say that 4 is congruent to 5? They're all congruent to each other, aren't they? All right. So that's my plan. Then I can use the same kind of reasoning to get the other pair of alternate interior angles congruent. All right. Statements and reasons. Let's start by saying that A is parallel to B. We know that's true because it's given to us. Okay. Now, angle 2 is congruent to angle 4 because of the corresponding angles postulate. So on our figure, we can do that. And then what do we say next in our proof? Yeah. Angle 2 is congruent to angle 5 because of the vertical angles theorem. And it seems reasonable that at this point we ought to be able to say that angle 4 is congruent to angle 5, but we got to have a good reason, okay? And a reason that we haven't used much up until now that gets used quite a bit, actually, in a lot of proofs, is substitution. The reason we can say that angle 4 is congruent to angle 5, and this is a little complicated. Let's pretend I haven't written that down yet. Let's pretend that I'm going to rewrite statement 3, okay? I'm going to rewrite statement 3. I'm going to say angle 2 is congruent to angle 5. But the substitution property says that if two things are equal, they can replace each other anytime you want them to. So, since we know that angle 2 and angle 4 are the same size, replace angle 2 with what it's equal to. So that's substitution. That's how I get angle 4 congruent to angle 5. Okay? Does that make sense to you, that that's substitution? Now, and I got to tell you too, some books won't let us do that. Some books claim that substitution only works for equalities, and they would make us change our congruent angles to the measure of angle 2 equals the measure of angle 4 and all that, and then do the substitution, and then switch it back to congruent. And that used to be the only way anybody allowed you to do it. They're kind of getting more lenient, and they're saying we can substitute with congruences, not just equalities. Question? Well, it's not really transitive. Transitive would be A equal to B, B equal to C, so A equal to C. So this is more like A equals B, A also equals C, so B equals C. So it's a little bit different. Okay? Questions? Now you can see what I've got covered up, right? I'm doing the exact same reasoning with the other pair of alternate interior angles. So I'm going to go back to statement 2 and add on to there. 6 is congruent to 8 because of the corresponding angles postulate. Then I'm going to say 3 is congruent to 8 because of the vertical angles theorem. So then I'm going to rewrite statement 3 again. I'm going to say angle 3 is congruent to angle 8, but I'm going to replace angle 8 with what it equals from the step above, which is angle 6, to get that. So, what do you think about the proof of the alternate interior angles theorem? Not so bad? All right, any questions? Are we ready to move on? All right, the triangle angle sum theorem. We're going to prove that the sum of the measures of the angles of a triangle is 180. All right. Now, on this proof, we're going to need an auxiliary line. Okay? Remember what an auxiliary line is? It's one that we add to the drawing just to make things easier, to make the reasoning we're going to do a little easier. So we draw in that line through point A that's parallel to segment BC. Okay? So we've got that. Now, what we want to be able to do is we're going to have to prove that the three angles inside the triangle have a sum of 180. That's going to take a little work, but look, in fact, maybe I don't even know how to do that without this auxiliary line, but look what the auxiliary line's given us. By drawing in, then, angle 4 and angle 5, do you think we can probably state that the sum of those three equals 180? And it'll be just a bit complicated because we never had a statement, a postulate or a theorem that says if three angles add up, or if three angles form a straight line, that the sum of their measures is 180. We never had that, okay? So we're going to have to kind of piece it together. But if we're careful, it seems like we ought to be able to do it because we know it's true, right? All right, so if those three add together to 180, then look what else I can do. Parallel lines, transversal, so angle 1 is congruent to angle 4, so I can do a little substitution there and change angle 4 into angle 1. Transversal over here, so 3 is congruent to 5. I can do some substitution there. So I can go from having 4 plus 2 plus 5 equals 180 to having 1 plus 2 plus 3 equals 180 by using substitution. You see the plan? Now, let's see if we can pull it off, which I bet we can since I copied it from the book. But you never know. Maybe I'll mess up uncovering it with the little screen. You know, there's still a lot of things I've got to do right up here. Okay, so all we're given is triangle ABC. That's it. Now, our whole plan is based upon that auxiliary line being parallel to line BC. If it's not, then I can't do that substitution that I've planned out. So statement 2, I'm going to draw line AD through A parallel to segment BC. And that's the parallel postulate. The parallel postulate says through any point not on a line, there's exactly one line through that point parallel to the given line. Nice that we call it parallel postulate instead of having to write that out. So there's one line through point A that's parallel to line BC. And we drew it. All right. Now, the next part of our plan, we want to get to the point where we have these three added together to equal 180. All right, so let's get started on that. Angle 4 and angle BAD. So look, this is angle 4. This is angle BAD. They do form a linear pair, don't they? How do we know they form a linear pair? We know what a linear pair is. So definition of linear pair. Well, if two angles form a linear pair, what do we conclude about those two? They're supplementary. So angle 4 and angle BAD are supplementary. Now we can write out like we did in a proof just a minute ago, if two angles form a linear pair, they are supplementary. But if you happen to remember that that theorem was called the supplement theorem, you can just write the supplement theorem instead. Now if you don't remember that's what it's called, then, you know, write out if two angles form a linear pair, then they are supplementary. Well, now that we've stated that those two angles are supplementary, what would we conclude from knowing that those two angles are supplementary? That their sum is 180. So the measure of angle 4 plus the measure of angle BAD equals 180. Why is that true? Because we know what supplementary angles are. So the definition of supplementary angles. And now let's pause. We go back to our plan. Our plan wasn't to get the measure of angle 4 plus the measure of angle BAD equals 180. It was to get the measure of angle 4 plus the measure of angle 2 plus the measure of angle 5 equals 180. So, how are we going to turn this into the measure of angle 2 plus the measure of angle 5? Yeah, but before we do some substitution, we're going to have to point out that measure of angle BAD is the measure of angle 2 plus the measure of angle 5. How do we know that the measure of angle BAD equals the measure of angle 2 plus the measure of angle 5? I don't remember saying this theorem or this postulate name in a long time, but I've said it a bunch of times. You'll know it as I say it. Angle addition postulate. So, the measure of angle BAD equals the measure of angle 2 plus the measure of angle 5. That's the angle addition postulate. Now, usually we've used that with numbers, right? If we had a 90-degree angle broken up into 30 and something else, we would say, oh, the angle addition postulate says it has to be whatever you add to 30 to get to 90. You know, we've done it that way. But the measure of angle BAD equals the measure of angle 2 plus the measure of angle 5, because that's the angle addition postulate. Now we use substitution. Replace, so rewrite statement 5. I'm going to rewrite statement 5, but I'm going to replace the measure of angle BAD with what I now know that it equals. So I'm going to replace what's in the blue circle with what I just underlined in blue. You with me? So that becomes the measure of angle 4 plus the measure of angle 2 plus the measure of angle 5 equals 180. And whenever you replace something with what it equals, that's substitution. All right, now, we need more substitution. I want to replace that and that, don't I? I want to replace the measure of angle 4. Since angle 4 is congruent to angle 1, I want to replace that with the measure of angle 1. And then since 5 is congruent to 3, I want to replace the measure of angle 5 with the measure of angle 3. And once I do that, I'll have exactly what I set out to prove. So I got to be careful, though. I can't jump the gun. So first, use the alternate interior angles theorem to point out that angle 4 is congruent to angle 1. And since it's the exact same reason and thought process, go ahead and point out that angle 5 is congruent to angle 3. And here is where I will agree with the being really picky part here. Since I have two different styles of notation going on, in step 5, I have measures added together. In step 8, I have angles congruent. I don't really need to substitute a congruence statement into an equation. Congruence to congruence, I'm fine with. Equation to equation, yes. But congruence to equation, there's not many mathematicians going to let you do that. But that's okay. It's easy to change, right? If I know that two angles are congruent, don't I know that their measures are equal? So the next statement is going to be that the measure of angle 4 equals the measure of angle 1, and that the measure of angle 5 equals the measure of angle 3. And how do I know that's true? I know that if the angles are congruent, their measures are equal because I know what it means to have congruent angles. In other words, I know that's true because of the definition of congruent angles. All right, so now we substitute. We're going to rewrite statement 7. But instead of the measure of angle 1, instead of the measure of angle 4, we're going to put measure of angle 1 because they're equal. Instead of the measure of angle 5, we're going to put the measure of angle 3 because those two are equal. So rewrite statement 7, but replace the measure of angle 4 with what it equals, which is the measure of angle 1. Leave the measure of angle 2 as the measure of angle 2. Replace the measure of angle 5 with what it equals, which is the measure of angle 3. And then leave 180 as 180. Oh, that's a good one, huh? Now, I admit that I'm more of a math geek than your typical person, but isn't it kind of cool we can prove that's true? I mean, isn't it? I think it is. I mean, here we are, just lowly high school students, and we can prove a theorem. Not just a theorem that everybody that ever takes geometry knows, and we proved it. So, all right, questions? And you would have thought that up all by yourself, right? Yeah, just nod your head and say yes. Last one we need to prove, the isosceles triangle theorem. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. And I like the book proof on this one too. So, all we're going to be given is that we have triangle LMP. And now, since we need two congruent sides, that's got to be part of the given, right? So, you just pick two of the sides and say they're the congruent ones. So, segment LM is congruent to segment LP. That's given. I mean, it's given, but you got to realize we're doing the giving, aren't we? We're deciding what's given. And how do we decide it? Because it's got to match the hypothesis of the theorem. We've got to have two sides of a triangle congruent. So we made it two sides of the triangle congruent. And then we've got to prove that the angles opposite those sides are congruent. Well, if we're having those two as our congruent sides, then these are the angles opposite those congruent sides, aren't they? So that's how, I should have pointed this out earlier. You know, we're making the given. We're giving it to ourselves. And we're deciding what's given by what the hypothesis, the if part of the theorem is. And we're deciding what we have to prove by looking at the conclusion, the then part of the theorem. Okay? So we're making this up ourselves. Now, making it up implies that we're deciding what's given and what we have to prove ourselves. Okay? All right. The only part of this proof that I don't like very much is the first step. Okay? And hang on. Do I need to? No, I don't think you need to know that yet. All right. So here's what the book does, and I've researched this a little bit on the internet, and this is pretty much the way everybody does it. I've got one that's different. I'll show you later if you want to see a different one. But we start off by drawing in that segment LN. But before I draw in segment LN, I need it to be a special thing. Okay? I need for N to be the midpoint. So, let N be the midpoint of segment MP. The reason is, and here's where here's what I don't like a whole lot about this step. We've never had a statement before that said every segment has exactly one midpoint. It's not a postulate that we've had. It's not a theorem that we've had. It's obviously true, but we've never stated it before. So that makes me a bit nervous to be putting something in a proof that we've never discussed before. But it is obviously true, isn't it? Okay? So we'll say that that's a postulate. It's a postulate that our book has never stated for us, but it is a postulate. Okay? So it does fit into our categories of reasons we can use when we consider that it's a postulate. Now, if N is the midpoint of segment MP, then I want to draw in that segment LN. So draw an auxiliary segment, or you don't even have to use the word auxiliary if you don't want to. Just say draw segment LN. And the reason the book gives is 2 points determine a line, which is a paraphrase of the postulate that says through any 2 points there's exactly one line. So I kind of prefer through any 2 points there's exactly one line. But if the book says 2 points determine a line is good enough, then who am I to argue? Okay? But 2 points determine a line is a paraphrase of the postulate that says through any 2 points, there's exactly one line. All right. Now that got us started. So I don't think we would have thought of doing this to get started. Okay? But now that we have, let's make a plan. You know how in several of our proofs that we did back in chapter 4, we would prove 2 triangles are congruent, and then after we proved 2 triangles are congruent, we would say, so segment whatever is congruent to segment whatever, definition of congruent triangles. Or angle whatever is congruent to angle whatever, definition of congruent triangles. That's what we're going to do here. The triangle at the top and the triangle at the bottom, because now there's 2 triangles, there's not just triangle LMP anymore, there's 2 others now. They're congruent to each other. Look how. All right? Those are congruent. If N is the midpoint of MP, those are congruent. LN is congruent to itself. So those triangles are congruent by side, 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 aren't they? Then we can say, oh, then the corresponding angles are congruent. M and P are congruent by definition of congruent triangles. You with me? Okay, so getting started on this proof, I'm not so sure we would have thought of doing this. Okay, but once we've got this, we're in pretty good shape. So, segment MN is congruent to segment PN. The book calls it the midpoint theorem. We always call it definition of midpoint. And I went back yesterday and looked at our definition of midpoint to make sure I was right that we can use that, and I am. The book, at the time they give us the definition, they state that means that the length of MN equals the length of NP, or segment MN is congruent to segment NP. So it is the definition of midpoint as well as midpoint theorem. Okay? Then segment LN is congruent to segment LN, reflexive. And something the book does, we usually don't. You notice we've never put that segment LM is congruent to segment LP into our proof. We always do that first. And I'm going to stick to that when I do them myself. But what the book does here makes perfect logical sense. They're stating that segment LM is congruent to segment LP right before they get ready to use it. So logically, I can't argue with them. They're exactly right. That makes sense. I'm just afraid, because didn't you kind of think we'd already listed that? You forget to list it if you don't use it immediately. If you don't list it immediately and use it immediately, sometimes you just forget that you haven't written it into the proof. Okay? Well, like we did in our plan, we now have congruent triangles because of side, side, side. So triangle LMN is congruent to triangle LPN. Reason is side, side, side. And now that we have congruent triangles, angle M is congruent to angle P. The book says CPCTC. I say definition of congruent triangles. You don't have to put both. Either is fine. Can I hear a woohoo? Okay. Your assignment is to make sure you can do all 4 of these learning targets. So prove without looking. Now you can look if to help you get started or to check yourself, but don't just copy them. I mean, what's the point in that, right? So prove without looking the vertical angles theorem, the alternate interior angles theorem, the triangle angle sum theorem, and the isosceles triangle theorem. If you get stuck, yeah, you can glance back at your notes and say, oh, okay, I remember now. We drew that auxiliary line. So peek if you're completely stuck, and then try to finish it out on your own. Okay? So there.